2-7, day 1. Topic is solving nonlinear inequalities. There's a couple different ways you can go about this. You may find for these notes in class that I'll show you a couple different ways. For these notes, I'm going to stay with a very graphical approach to solving them. Okay, just because all throughout Chapter 2 we've done a lot with graphing, polynomials, and rational functions, and by nonlinear, I mean that shouldn't be a surprise. Everything in Chapter 2 has been nonlinear, right? Quadratics, cubics, rationals. That's been the whole theme of Chapter 2. We've worked hard on producing graphs, and I want to stay consistent and give you as little new stuff as possible, right, to solve these inequalities. So that's the approach I'm going to take, and we're really going to stick with that graphical approach. One final word on the title page here, kind of funny. It's nonlinear. I should have picked my picture better. They're inequalities, no doubt about it. They're linear, though. Those are lines forming those inequalities. So the graphs we make aren't going to look exactly like that because, again, nonlinear is always synonymous with curves. So we're expecting more graphs that are curved. All right, first slide here, we're going to do a quadratic and then a cubic. Okay. All three examples we're going to do today, the instructions are to solve. Okay, that's all we're after. As far as the sign that we have, it is a less than sign. Okay, I'm looking right here. It's a less than sign. Okay, an important thing to start with that we're looking for is like the question that we're trying to answer. Okay, it's not just, yeah, we're solving that expression. That's fine. Okay. Another way to put that, though, is we are searching for x values. That when you plug them into that quadratic, that you get negative y values. Okay. This is a less than sign. What numbers can we put in that quadratic that will give us negative y values? Okay? Again, that's because it's less than 0. What I'm going to do to start, though, and you'll see this comes up quite a bit. I just simply want to find the zeros. That's always a great place to start. We've done that time and time again throughout this unit. This one is factorable. If you get a quadratic, you could expect most of them to be factorable. If they're not, just go to the quadratic formula. But there you go. It's got 2 zeros at 3 and then 1 at -2. So I'm going to mark those. And here you see over here I'm making a little sketch because I'm taking this graphical approach to it. But notice I called it a sketch. We've said that there's a difference for us that, if we get instructions that say to, produce an accurate graph or to make an accurate graph, then we're going to worry about details. Sketches we don't. Okay. In all these examples, you're going to see me doing sketches. I don't even have it on graph paper, right? That's not the point. I don't need it to be accurate. With that, combined with the fact that I could look at my leading term and see this is a quadratic that has a positive leading coefficient. That's big for us because it tells us it opens up. And that quadratic is really sufficient for what we need. It really is, okay? Because now I can just observe it and I can figure out where it's negative. All right? Keep this in mind. This axis right here, the horizontal axis, this is the cutoff between positive and negative y values. If I'm up here, you have a y value that's positive. If the graph is down here, you have a y value that's negative. Okay? And now as I see that, I look to right here, and it's in between. Those x values in there are going to give us the negative y values. Okay? Now, where it changed sign from positive to negative, that involves the zeros. Okay, so even those, x equals 3 and x equals negative 2, those aren't our solutions. We still really needed to know those numbers. It's yet another case with a polynomial where you just got to be able to find zeros. Okay, got to be able to find them. Okay, now how do I say this? I've got an interval that's got a starting point and an ending point. Okay, so you'll see that notation come up a lot. You'll see that right in the middle. Okay, my starting point, though I'm not including it, was at negative 2, and then my ending point was at 3. You can put in any value that you want in between that interval, and that's the only interval, and you are going to get negative y values, which again are less than 0. That's what gave away for me that I want negative y values. Okay? That was a quadratic. Let's hop down and take a look at a cubic. Okay? The idea is going to be the exact same. I need to produce a little sketch. Doesn't have to be awesome. Okay? I need to know where the zeros are. And, I need to do the leading coefficient test. Okay, so already I'm hoping you're looking at this and thinking, that's a cubic. The tails are going in opposite directions, and you've got a positive 2 out front, so the left one's going down and the right one's going up. Okay, that's going to be part of it. One other thing that this one has that the other one didn't, in addition to being a cubic, is you shouldn't try to do anything until you have one side as 0. So I'm going to add that 48 to both sides. And notice we now have a greater than sign. So when I get to my graph, I want the intervals where this graph is positive. Okay? Let's already mark that, because I find this is the biggest part where students struggle on the concept side. Is that after you produce your sketch, a lot of times things kind of break down and you're like, oh, I made a nice little sketch, but I'm not making the connection as to how this sketch helps me answer the question. Positive y values are above that line. Negative y values are below. Now at this point, the goal would be to get some zeros. However, we would need a table on the calculator here because we're not going to factor. We can't use the quadratic formula. We'd have to use a little bit of synthetic division. Okay, and that's the approach that we would take. Okay, it's going to have 3. Okay, so as you're seeing, and again, you could list out all the factors of 48 over all the factors of 2 to get some good values to check. But they end up being 4, negative 4, and 1.5. And again, don't think that those numbers are just magical that randomly appeared. Again, if you wanted to get to those, use your calculator, make a good table. Okay, the rational zero test would tell you you're going to need to look at a few fractions because numbers, and there are certain rational numbers that are in increments of a half that we would have to check. And as always, when I go to the table and get that 0, I still need to verify that it's a 0 using synthetic division. Sure enough, we get no remainder. 4 is a 0. Oh, I mentioned another one was negative 4. Again, you would be able to see that one in the table. And 1.5, or 3 over 2, which would be 3. All right, so we have verified them. We've got 3 zeros. Let's go mark them on our graph. We had one here, one at 1.5, and another one at 4. I already talked about the tails. Left is going down, right is going up. Okay, cubic with 3 distinct rational zeros. Okay, should be thinking to yourself, do we have any bouncers? Okay, for this to fit, the answer has to be no. We have to be talking about crossing, crossing, crossing. Okay, and the end result is a graph that isn't very good. But you know what? It's good enough. Okay, it's going to do what we need it to do. All right. Now remember here, positive, 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 positive. Okay, I've got that green line marked. We want to refer to the parts of the graph that are positive. Okay, I'm starting with that left tail, and I'm saying no, right down here. Not using it. Now, at that 0 we cross, this interval of the graph seems very important. Okay, I'm going to need to refer to where that starts and where that ends, because at that point the graph is positive. It goes back negative, and then we get this tail right here, which goes off and goes positive. And again, from what we know about cubics, we know that tail is going off positive, and it's not coming back. Okay, it's not coming back. All right, so I have 2 separate intervals that I have to say. The first of which has a start point and an end point. We're talking strictly positive, so I don't want to include these points. But from my zeros, I would say -4 and 3 over 2. Okay, again, what that means is if you go back to this big long cubic that we started with right here, you plug in any number in that interval, you're getting a positive answer. Okay, that's what that means. You put any number from -4 to 1.5 in, you're getting a positive answer. Okay? Once you get to 1.5, that changes until we get to 4. And from there, you can put in any number that's bigger than 4, and you're also going to get a positive answer. Notice the difference here is that I have 2 separate intervals. On the quadratic example, we just had the 1, right? It was from -2 to 3, and that was it. So I could summarize all the solutions in one interval. This one had 2 separate ones that were not connected, so I had 2 inequalities where I had to say it. All right, example 3, this will be the last one for lesson number 1 here of 2.7. It's a rational, okay? It's a little bit different, sort of. We're still going to make a graph, okay? We still want to know zeros, okay? The only new element that we get with a rational graph is that there's these other points where the graph could jump from positive to negative. Because again, I'm going to go right on here and say, here we go, here's our cutoff. Up here, you've got y values that are positive. Down here, y values that are negative. Now this is interesting. This is a less than or equal to 3. And the others we had kind of switched. Well, the first one we didn't have to change. The second one we did, so that one side was 0. And we should take the exact same approach. We'll get something like that. Okay, but I was saying earlier about the graph changing sign. Rational graphs can have asymptotes. Okay, and the ones that we're particularly concerned about right now are the vertical ones. We got to know where those are, as always. And again, this is why I'm trying to set this up so that we're not doing a ton of new stuff. Right? We've known, since the first time we saw rational graphs this chapter, we got to know where the asymptotes are. Right? They tell you so much about a rational graph in terms of what's going on with the 2 variables. Okay, it's the same. So we're taking this approach where we're putting together a decent little sketch, not a great one, but just a decent one. Okay? Now, not everyone is going to be like this, because it could have just been less than or equal to 0. But when I move over that 3, I've got a little extra work to do here, because these two terms, the rational function I have, 2x minus 7 over x minus 5, and then I'm subtracting 3, those need to be combined. Now, one of these is a fraction, so anytime I'm subtracting fractions, I have to have a common denominator. Things get a little bit weird here, because the denominator I have to use is already chosen for us. It's x minus 5, okay? So that starts to look a little confusing, but keep in mind, all that happened is I took 3, I should say negative 3, and I multiplied it by x minus 5 over x minus 5, okay? I know I'm still going to have x minus 5 on the bottom. It now becomes, what'll you have on the top? I should distribute that 3. And now we just have some like terms on the top to combine. 2x minus 3x is negative x. Now you got to be careful with the negative signs here. Negative 7 minus negative 15. That's like negative 7 plus positive 15. And we get 8. Okay, this down here, that's what we're going to try to graph. Okay, and that's going to work out much better. One side is 0, and we just have a single rational term on the left. Again, in your homework, not everyone is going to be like that. Okay, some of them I will give you, the expression that we got to that's boxed in down here. Some of them will just start with that, and you won't have to do this work. Okay, you should be able to, but I'm not going to make you do it every time. Okay. As always, with rational graphs, the issue becomes asymptotes. Okay? I always find my vertical ones first. They never vary in how you find them. There's one of them. For the horizontal, we have 2 first-degree polynomials. They're both lines, both to the first power, which means I go to the coefficients in front of those. The top one is a negative 1, the bottom one is 1, and we get negative 1. Slide this down a bit just so I can see a little more of my graph. So over here, I'll just put a dashed line. Again, this doesn't have to be super accurate. There's x equals 5. There's y equals negative 1. And again, we know with these two lines, this rational graph will always be approaching both of those lines, never crossing, never even touching. Okay? Always approaching, never crossing, never touching. And we have to check points. Okay? We get to the point here, we have to check some points. 6, I always start right here. Stay away from 5. Okay? Stay away from 5. If you were to check 6, you'd see that this part of the graph is up here. And if you were to check 4, you would see this chunk of the graph is down here. Okay? So, we're getting close. All right? Now, I go back to that rational graph that's in that box in the bottom left. Okay? I'm looking for the x values that are either negative. Okay, so with that green line that I marked, I'm thinking below. Okay, not above, below, or possibly on it. Now that's interesting because I look right here and I see we do have one point that's actually, like, it does cross that green line. Okay, and at that point, the y values are switching from positive to negative, but I actually don't know where that is, which is a bit of a concern. I'm going to need to figure that out. All right. Now, if I kind of look at these as two separate curves, okay, two non-continuous curves separated by this asymptote, I'm looking at the one on the bottom left, and I notice that that entire part of the graph, is negative. It's below that green line that separates the positive and the negative y values. It's below the whole time, which means as far as stating my solutions, I want all of those. I want all of them. Now I don't want to say 5 because that's an asymptote, right? So that's why I have that point marked. The graph is never going to take on the x value of 5, or at least if it does, you won't get a y value. So any x value less than 5 is going to be a solution. And here you see why I have to be aware of the asymptote is as soon as you cross x equals 5, the graph jumps up and is now positive. It's now above that green line. And I come back to this point right here where it crosses back to negative. Okay? I really need to know where that point is. Okay? I really do. We haven't really talked about this with rational graphs yet. We probably should have at this point. What's happening here is it's a 0. And to get that 0, what we have to do is take negative x plus 8, set that equal to 0. You solve it and get that x equals 8. Notice if you go back to that boxed-in rational function that we're working with, negative x plus 8 over x minus 5, it's the 0 at the top. Okay? We need to know those two. When we were making rational graphs, we weren't super concerned about that point. Okay? Now, if we're going to be picky about, positive or negative, we need to know where it crosses. That's always how you could find it. Okay? It's basically like if you see a 0 or where it's crossing the x-axis, you just need the zeros at the top as well. Okay? And that's what it is. And here's what it tells me. The other part of my solutions. And it does say less than or equal to 0. So notice on the second one, I'm including 8. If you plug 8 into our function, you're going to get 0. And it says to include that, less than or equal to 0. So if x is less than 5 or greater than or equal to 8.